Okay, so now we're going to go through and do kind of some intuitive practice here to see what's going to happen when we put our salts in solution. Are they going to make something that's acidic, something that's basic, or something that we can't tell? So let's start off with our first list here. What I want you to do is go through here and break everything into its ionic components. You're going to actually want to be pretty comfortable doing this. It's going to save you in dividends later, especially when we get into electrochemistry, and it's going to make things a lot faster for you for kind of predicting what your products are going to be. So first go ahead and do that, and then see if you can't recognize who your strong acids and bases are. So therefore, being able to predict, are you going to make something that's acidic, basic, or neutral? Okay, so let's see. It's going to do it for me. So this is going to give me K plus and ClO4 minus. This gives me ammonia and chlorine. This gives me sodium. I'm not worried about how many right now. And SO4 2 minus, so sulfate, sodium, and HSO4 minus, and potassium, and sulfur, lithium, and carbonate, HCO3 minus. Boom. Why, that was quite a dramatic little minus there. All right, now I'm just going to go through and pick out the things that I instantaneously recognize, and I know that any of my +1 ions will bond with a hydroxide to make a strong base. So if I put them in solution, they're not going to reform that strong thing. It's defined as strong because it's going to dissociate. Same with Cl, because that would make my HCl, and then I'm missing somebody. Who am I missing? Feel like I'm missing. Oh, ClO4. Yep, would make HClO4. So the answer to this one is no change in my pH. Neutral. And I'm going to write out the first couple of reactions so we kind of get a feel for them as far as saying, do I know that it's going to make something more acidic or basic? We've done this one a few times. Plus water. What's this going to do? Well, the only thing it can do is donate a proton, so I will end up with ammonia, NH3 plus H3O plus. So this is going to make it more acidic. And then for my sulfate, SO4 2 minus, the only thing it can do with water is accept a proton. And you might be a bit freaked out because you're thinking, but H2SO4 is a strong acid, which is true. HSO4 is a weak acid, so I will get some of that. My water has now donated a hydrogen, SO4 minus, and now I have OH minus. I forgot my plus here. Cool. So what is this going to do? It's going to make it basic. So if I can look at something and say, is it going to accept or donate a proton, and recognize immediately that it'll do either of those, I don't need to do any more work. I will know whether or not it's going to make it acidic or basic. So the HSO4, we just talked about that one. We said that it can't accept another proton, right? Because that would be a strong acid. So the only thing HSO4 can do is donate. So plus H2O is going to donate. So this is going to be my weak acid. Therefore, it's going to make this acidic. So I'll get H3O plus SO4 2 minus. Okay. S2 minus, the only thing it can do is accept a proton. So S2 minus is going to go to like HS minus. So what have I done? I've taken away a hydrogen from water. I'm making a base. So this is making it more basic. HCO3 minus. Ooh, this one is amphoteric because I can give up that hydrogen or I can take it. It's HCO3, not HClO4, so it can be either. I can go HCO3 minus plus water going to H2CO3 plus, let's see, I've taken a hydrogen away, so this is going to make a basic solution. So this is acting as my weak base. Or I can have it acting as a weak acid, HCO3 minus, where it's going to donate a proton to the water to make H3O plus my carbonate ion. 3, not 2. 2 minus. Cool. So what do I got to do? I got to see, is my Ka larger than my Kb? Because if my Ka is larger than Kb for HCO3, then I am going to have something that's going to decrease the pH. I would need to know that. If my Kb is larger than my Ka, then that means I'm going to increase my pH. Does that make sense, hopefully? Okay, let's give it another go. Do the same thing, and again, break things into their ionic pieces and see if you can't recognize what's going to do what. Again, don't need to worry about writing out the reactions. I'm only doing that to help you with a little pattern recognition, so you kind of get it really built into there. And if you can look at something and you know that it's going to form a strong acid or a base, you don't need to do anything. You can cross it out and be like, nothing. All right, LIBR, well, that kind of gave up the ghost. At least I, whoops, go back. LIBR neutral, why? Lithium and bromine. One would form a strong base, the other would form a strong acid. Let's cross out anything that we know won't do anything. And neutral, because I would make a strong acid and a strong base. And then everything else, now my ammonia, we've done this a bunch of times now. This is NH4 plus, so the only thing it can do is act as a weak acid. So this would lower the pH. My SO3 minus, well, that would be a proton acceptor, so this would be my weak base. That is why this would raise the pH. That is why we need to know the Ka or the Kb to decide. So in this case, I would need to know the Ka for ammonia and the Kb for SO3 minus, and whichever one is larger is going to be the dominant thing, the thing that's going to have the most impact on the pH. Okay, CO3 minus, CO3 2 minus. Well, that thing can only accept a hydrogen. So what does that make it? It makes that a weak base. So therefore basic. Let's see, we've taken the bromine away. We just did this one. Yeah, we just did this one. I was feeling like a little bit of deja vu. The ammonia is going to donate a hydrogen. Yes, we did just do this one. Do I have a duplicate? Or have I just done this lecture so many times now? I think that's the case. My darn dogs haven't been cooperating today. All right, so now that I've lost my train of thought and I'm worried that I don't want to leave something off, let's just remind you about what's happening with this ammonia structure. So I have something like this. There's my 3 hydrogens, and here is my C6H5 hanging out here. So I'm not going to break this covalent bond between nitrogen and carbon. And those hydrogens here, these are all bonded to the carbon. So the only thing I can do with this is break a nitrogen-hydrogen bond, making this a weak acid. It's a weak acid, therefore it would make it acidic. And ammonia and HSO4, so both are a weak acid. How is that? Because HSO4 can only lose a proton. H2SO4 is a strong acid. So this can only go to SO42 minus. right? So that makes this only capable of being a weak acid. I can't accept one. NH4 plus, ammonium, only thing it can do is act as a weak acid. So even without looking anything up, I would know that this would make it more acidic. And let's see what's going on here. Forgot to cross out my potassium. So that leaves me my CH3COO minus. These hydrogens are attached to that carbon. So what do I have structure-wise? I have something that looks like this. And then I'm going to go to a carbon and then to my oxygens. So what does that tell me? These hydrogens aren't going to come off, so that is not going to be acidic. That means the only thing this is going to happen is I can accept a hydrogen, the bond to one of those oxygens. So it is going to be a weak base and therefore make the solution more basic. Okay, so practice that with that yourself and you will get fast at it to where you can kind of just start knocking off and predicting what your products and reactants are. You do want to be able to look at these things and get the correct ionic charges on things, so don't blow that off. And then Wednesday, we'll bring it together. We have a couple practice problems we'll work on together, and it's going to be all sorts of fun, I promise.